Hello guys, welcome to yet another video, and today we're going to be looking at a full paper for term 1 in physical science. Okay, this is a paper that was written in the KZN province last year, so this should sum up all the work that we've been doing. All right, so let's just rush into this, not waste any time. So what is important, guys? I mean, you're given the topography of the paper and how to behave in the paper. That's for me not a big deal. But what is important is to show all formulae and substitutions. Okay? In all calculations, not just in, haphazardly, but you have to do that. And then to round off your final answer to a minimum of 2 decimal places. So you see, given all operational instructions, which is quite important, so this and that and this one is what makes up the key. Okay, give brief motivations, discussions, and my favorite part is etc. Okay, where required. Okay guys, let's not waste any time and get to the business of the day. Okay, so we're going to have a bit of a multiple choice. Remember, despite general instructions, you read the local ones because they take precedence over general. But if there's nothing, general instructions kick in, isn't it? Various options are provided as possible answers. Okay, I like this part, possible. To the following questions, choose the answer and write only the letter next to the question number in the answer book. Okay, and you're given an example of how this looks. Okay, 1.11, the answer is D, so you're only choosing one letter, not more than one. Okay, let's get to it. Now 1.1 says, according to Newton's second law of motion. Okay, what are we talking about? Newton's second law of motion. And now we're talking a parameter. Acceleration of an object is, okay, now you just revise Newton's second law. All we know, there's 2 proportionalities in Newton's second law. So the acceleration is directly proportional to the force. Acceleration is inversely proportional to the mass of the object. Alright, now I told you the acceleration is always equal to its mass. It's not really equal, but it's proportional, inversely proportional. So that's not true. Is inversely proportional to its mass. That's correct, okay? Directly proportional, not really directly, but inversely proportional. So that's not true. Is independent of its mass, not necessarily. As much as it is directly proportional to the force, it is somewhat dependent on the mass, because the heavier the mass, the lesser the acceleration for a given resultant force. Okay, but you can play around that as well. So the best answer then becomes B. Okay, I'm sure you can see that. Next one, a ball moving horizontally hits a wall with a speed of 2v. Okay, the ball then bounces back horizontally with a speed v. Okay, as shown in the diagram below. Once you see a ball and the wall, think of the impulse equation, because there's going to be an impact here. Okay, is equal to the change in momentum. There's definitely going to be a change in momentum. But what you can notice that the initial momentum here was kind of 2v. The initial velocity and the last velocity is v. So you can say kinetic energy is not really conserved. But we were not told anything about this system so far. So we can just say probably only linear momentum could be conserved, but kinetic doesn't look conserved. Okay. And then let's look, which one of the following combinations regarding the linear momentum, so this is the parameter we thought about, and total kinetic energy, Now, don't you see that we're having a situation here that this question looks similar to the one from the Freistaat? So it looks like KZN is in cahoots with the Free State. Hey? They're doing the same thing or similar things. But that's good. It's a collaboration. Okay, of the ball. Okay, what are we saying here? Which one of the following combinations regarding the linear momentum and total kinetic energy of the ball for the collision above is correct? Assume that the ball wall system is isolated. Okay, now that is something that is something critical now. Now we're forcing matters instead, because remember, this was not necessarily showing us an isolated system, but now we are forcing it that this is an isolated system. Now, if this is an isolated system, it means both linear momentum and kinetic energy are conserved, isn't it? So that makes sense. Okay, now which one of the following is correct? We say linear momentum will be conserved in a closed system. Should be conserved. This one is incorrect, because now we finally created a kind of a forced isolated system, really. Kinetic energy, unfortunately, because of this system being isolated, should be conserved. Anything otherwise is not correct. So what is the best answer here is A. Okay, so I'm sure you can see that. Again, here this looks controversial directly, but because of this statement, remember, certain statements carry more weight than just the general picture. So at times, look at the dynamics. That's why it's important to read all statements and put sense into the entire situation than just what seems to be too obvious. Otherwise, you would run into problems. Okay, I think that is fair. An object falls freely in a vacuum. Now, remember, we're talking about a free fall. Okay, and then secondly, we're talking about a vacuum. So what does this vacuum business mean? It means we are also creating a closed system, okay? So near the surface of Earth. And of course, you know that in a closed system, when you talk of a free fall, only gravitational force is acting. Okay, now which one of the following statements regarding the motion of the object is correct? All right, not a problem. Now the rate of change of velocity. Okay, now when you talk of the rate of change of velocity, what are we talking about? That is acceleration. And the acceleration in a free fall is the gravitational acceleration. Okay, so the rate of change of velocity of the object will remain constant. That is true, because we know G is constant in a vacuum. In fact, G is just G. So that is, if this is the resultant force acting on our object is the gravitational force, it already means that acceleration is constant. And acceleration is basically the rate of change of velocity, isn't it? So that's a good one. Now the rate of change of velocity of the object will increase uniformly. Okay, not the rate, basically. The problem is the rate here. Because we know that if we have a constant acceleration, it means the change of velocity, not the rate, but the change of velocity of the object will increase uniformly. So because we are saying the rate, we are now suggesting that acceleration will change. Acceleration is constant, so that is not true. But if we just took out the word rate, it would be true. Okay. Now the velocity of the object will decrease uniformly. The question is, does it actually decrease? It depends on the direction of motion of the object. On a free fall, if you're going upward, you are certainly going to be decreasing uniformly, which is true. But as soon as you get to the highest point or the maximum height, where the velocity has dropped to zero, it changes direction and starts increasing in the opposite direction. So it's not necessarily a decrease. So this cannot be accepted. the velocity of the object will remain constant. It does not remain constant because we are experiencing acceleration due to gravity. So it uniformly increases or changes. In fact, let's just say uniformly changes, but it does not remain constant. So what is the best answer here? Best answer is option A. Okay, so let's move on. The next question says, which one of the following compounds is saturated? Now in grade 12 syllabus, you know that saturated compounds are alkanes. Okay, you know that these are derivatives of alkanes, which is alcohols. Derivatives of alkanes, which is also esters. You can name them. I mean, there's lots of them. Maybe esters is not quite a good option, isn't it? Because we're seeing some double bonds, so the bonds are not. But anyway, when we talk of saturated, we're talking about the carbon chain specifically. So it's not about the substituents or Aibo. It's not Pelan. And then, of course, I would be cautious though when you're talking about esters here. You are talking about halo alkanes. Okay, think about those things. Now inspect what group of organic compounds. You can see here there's nothing else but just hydrogen and carbon. So these are hydrocarbons, so meaning we're talking about alkanes. So when you're talking about alkanes, we're looking for an alkane here actually, because now we can see these are all hydrocarbons. So of the hydrocarbons, only alkanes are saturated. So we want everything to fit into this formula, CnH2n plus 2, because that is the... I'm wasting time, guys, I'm sorry. I don't know. So we want everything to fit into this formula. Okay, so that's what we want. Now let's see. This one is saying CH3, 1, 2, 3, 4. There's 4 carbons. Then the hydrogens is 3, 4, 5, 8. So this one basically is only half of this, which is alkenes, okay? Because it says C2H2N. Right, so C4, 4 times 2 is 8, so it doesn't add the 2. So if it negates the 2, it is an alkene, so this is incorrect. This one is 1, 2, 3, 4, so again C4. How many hydrogens here? 3, 5, 6, 8 as well. So we've got H8 again. So again, this one only covers half of our formula, and that is alkenes, so that is incorrect. Just a moment. Alright guys, I'm back. Sorry for the interruption. That was an important phone call. Okay, now we're seeing that, okay, this one is not doing the things, right? So we can say, go, you're not the part of the business here. And then let's look at this one. Of course, this one basically, once you see something like this, it's a branch, okay? Usually, it is a branch. But if you see a subscript here, it just means it's part of the chain. But again, if it is going to have a subscript like that with a 2, it can't be a 3 if it is part and parcel of the chain, as you know. So if you see the number 2 after the H, and then outside the bracket you're seeing a subscript like that, that already tells you you are just multiplying a portion that is within the chain. But now because it has a 3 instead of a 2, okay, it's a 3, so this is a side branch, okay, remember that. So this is a side chain, so this is a branched alkane, all right? And then let's have a look at this branched alkane. It doesn't matter what it is after all, But how many carbons do we have here? 1, 2, 3, 4. Okay, so actually we don't have a 2 here, so let's go. I was just trying to refresh a few ideas there. So we've got 4 carbons, so this is C4. How many hydrogens? We've got 3, 4, right? Plus 3, that's 7. Plus 3, that's 10. Oops. Okay, so can you see that this one actually fits here, because C4, 4 times 2 is 8, plus 2 is a 10. So this one ticks the box. All right, it does everything. It does everything, and that's basically what we're looking for. All right, so this becomes a correct answer for a saturated alkane. This one is 1, 2, 3, 4, 5. Okay, 5. But do you see what is happening here? There's a 3 here. So this means there's dimethyl side chains here, because if it was a 2 and then there's this number here, we can accept it as part of the chain. But because there's a 3 and there's a 2 outside, it means there's 2 methyl groups in this one. So it's a branched alkene, because you can see the last carbon is CH2 instead of CH3. So it means there's a double bond between the last carbon and the second last, which you can regard as the first because you prioritize the functional group. So this is already an alkene by just looking at the structure. But again, you can check 1, 2, 3, 4, 5, 6. So we've got C6H. How many H's? We've got 3. And then this is 6, so we're going to have 9, 10, plus 2, we've got 12. So do you see it only goes half of our formula there, so it's an alkene, so it's definitely wrong. All right, so I know guys, some questions take a moment to do right. So for this one is a C. Okay, again, these are types of questions where you need to make 2 decisions because they are designed to stall you a bit. So you can decide if something needs a bit more, look into, then you decide whether you want to answer it instantly or you want to go on. But I mean, if you have an idea of how to answer it, you just have to answer it. Just a moment, I don't know why that. Okay, sorry guys, I'm getting interruptions today. I don't know why. Anyway, so as I was saying, these kinds of questions are designed to stall you a little bit, so you can decide if you're feeling like this is going to be a little bit difficult or a steep hill to climb, you can just move on. But if you feel you have an idea of how to get around it, please don't waste any more time, because you just have to do it so that you can speed up wherever you can. You don't want to come here and speed up and yet you had an idea and you get it wrong. Okay, let's quickly get to this question. Now the structural formula of an organic compound is given below. Okay, what we see striking is the triple bond to suggest that this is an alkyne. Now this already tells you prioritizing carbons to the side closest to the functional group. So this is already carbon 1 and carbon 2 and carbon 3. But now we don't know what about the other carbons. So let's check the longest chain. It's 1, 2, 3, 4, 5, 6, 7. So if we're choosing that bent one, it's 7 carbons. Let's look at the straight one. 1, 2, 3, 4, 5, 6, 7. It's also 7. Let's look at this one. 1, 2, 3, 4, 5, 6. Okay. So basically the longest chain is 7 carbons. And usually, if the straight chain works for the longest chain, keep it to that. Okay. Why should you suffer? And then of course we've got these 2 methyl groups. All right, so we have to think about them as well, but we already know that this is carbon 4, 5, 6, 7. Okay, now let's discuss what is going on here. We are looking for the IUPAC name of our molecule, and then we can already see that this is a hept 2-ine. Remember, the lower number of the 2 that actually bestride the triple bond. So the first carbon that you arrive at that surrounds the triple bond is your number for the bond. It's not the higher of the two. It's not the higher of the two. It's the lower of the two carbons that participate in the triple bond. All right. Again, so this is going to be a hept 2-ine. So let's look. Do we have a hept 2-ine? Yes, that is a hept 2-ine. That is a hept 2-ine. So those are already options. A hept 5-ine is already wrong. A hept 3-ine is already wrong because the mistake they're making, they're taking the higher of the two, and you don't take the higher of the two. You take the lower of the two carbons that participate in a triple bond. So you can see that you always need to identify where are the errors so that you can understand the tricks, because they will get you down if you don't pay attention. Now let's look at this. This is now a 5,6 because this is carbon 5, this is carbon 6. So a 5,6 dimethyl. So where do we have that? There is 5,6 dimethyl. So this one takes the crown because it numbers the position of our functional group, which is the triple bond, correctly, and it mentions the substituents correctly. It mentions the parent chain correctly. So this is the answer. Okay. Right. Now, why is this one wrong? Because it already says 5,6 dimethyl. The problem is the position of our bond, because it can't be 3. You're taking the lower of the 2 instead. So the only thing that makes this one wrong is this 3. Otherwise, everything looked perfect. So always be cognizant of such matters. This one is already wrong because the position here is messed up, isn't it? Because, I mean, where is the triple bond? The triple bond is not even on there. Okay, yeah, this one would have been carbon. If you said this is 1, 2, 3, 4, 5. So it means we did not prioritize. Here, we failed to prioritize the functional group in a way. So we just chose the substituents, which is not the case. The substituents don't take precedence, but they come after you've already prioritized your functional group. So that is the most important. Again, it's not exactly wrong, technically speaking, but it's just a rule, okay? It's bending the rules instead. Okay, guys, so I know I'm taking a bit of time to do this, but let's move. Now the next question says, consider the reaction represented below. Okay, we've got this molecule right here. So it's 1, 2, 3, 4, 5. So it's a pent something. But now, all these, yeah, if you have twos in between, this is an alkane. And specifically pentane. All right. And then we are then forming this molecule here. What does this molecule do? We're going to see C2, 2 times 2 is a 4, then plus 2 is a 6. So again, this is an alkane, because this formula describes these two. Okay, so this formula is describing this friend and that friend. Okay, that's why we know these are both alkanes. Now remember, if you're splitting an alkane, a longer chain alkane, to much shorter molecules, if we've already produced just 2 and this is an alkane, it means this one should be an alkene. Okay, because it's an elimination reaction. But this elimination reaction has a name. We call it cracking. Okay, this is cracking, which is splitting longer chain molecules under very high temperatures and pressures to produce these ones. Okay, now which one of the following correctly gives the type of the reaction? You can see the type of the reaction is elimination that takes place in the homologous series to which X belongs. We can see that X belongs to alkenes. So we're looking for elimination and we're looking for alkene. It cannot be an alkane again. It's not an addition. So which one ticks the boxes is D. So guys, this is how you score those marks. I know I took a moment here, which I wasn't supposed to, but it helps to give you a bit of an extra, so that you are confident. So let's just go on and tackle the long questions. Now here, this is Newton's laws of motion. Okay, almost always this question is on Newton's laws of motion. And in fact, most of the questions in physics, they have somehow an application of Newton's laws of motion. So you can't really stay away from them. They are like the umbrella of our physics. So if you ignore them, you are going to die alone, okay? Not with me. Okay, now let's look at 2.1. A crate of mass 4 kgs is being pushed to the right. So I always enjoy directions. Is being pushed to the right across a rough horizontal surface. Once it is rough, it means we're moving this object and we're moving it to the right. So most likely we're going to have Fk, which is kinetic friction, by a constant force of magnitude 10 newtons that acts at an angle of 30 degrees. So we know that theta is 30 degrees, the force is that, and we can see the diagram. So whenever I see this, I immediately break my force into components because it acts through components. I don't know. Sometimes it's a bit challenging. Okay. So I always break it into components. Of course, we know now if this force is directed down like that, then the vertical component, let's call this one FA, then this one is going to be F. Let's just call it F instead of FA. We know that the force is F. Yo, my F looks horrible. Okay, there's our F, and then this one should be Fy. Okay, because that is the vertical component of that force. That becomes Fx, which is the horizontal component. Always, a force that is not acting horizontally or vertically, just know it is acting indirectly through its components. Okay, those are the most important to make sure you show them. And then, of course, in this object, we still have our weight straight down. And then we're going to have our normal force straight up. At the moment, I'm not really interested in proportions. I'm just interested in the direction and the name of the force involved. Okay, so that's what we've got. And then, of course, you would remember that we're told that there's a rough surface, so there's frictional force. We don't really care about its proportions. So this is Fk. Okay, so these are all the forces acting on our object. All right, so we need to make sure we have them in order. Now you can already tell here that what is balanced here and what is not balanced. If we're moving to the right, it means this guy here, this guy is greater than this guy, because the horizontal forces will determine a horizontal motion. So it means our horizontal component of our force is greater than the frictional force, and that's why we would be moving to the right. That is key. Number 2, what else? It means our vertical component together with gravity should balance out our normal force, isn't it? Because these are directed down, so they will be additive in the same direction. This one is opposing them, but because this object is neither going deep into the surface nor being lifted off the surface, it means they're in balance either way. Okay, that's important. Now the question says state Newton's second law in words. Okay, so we've got 2.1.1. We want to Newton's second law. Newton's second law states that a resultant force applied on, just a moment. Alright guys, I'm sorry, I'm just getting interruptions. So we're saying now a resultant force applied on an object, okay, will cause the object to accelerate. To accelerate in sometimes what I don't know about target of in the direction of the resultant force, okay, such that the acceleration is directly proportional, okay, to the resultant force, and inversely. Proportional to the mass of the object. Okay. Yeah, I'm not really used to holding this pen, so in a way it's just doing some things to me. Of course, guys, I'm just simulating an exam. I mean, my writing is not impressive, so at the end of the day, you know what to do. So what we know is that there is a resultant force. What is important is that this force is a resultant. It's not just any force. If there's multiple forces, we're talking about the resultant, not necessarily the biggest of the forces. But obviously the biggest of the forces will be most likely the one in which the direction of the resultant force is going to go. Will cause the object to accelerate in the direction of the resultant force. Now you're going to capture these proportionalities, the direct proportionality between the resultant force and the acceleration, and the inverse proportionality between the mass of the object and the acceleration. So that's how you score those 2 marks. Easy. 2.1.2. What is the question? Now it says draw a free body diagram of the force, for the crate. Of course, this is all about the forces. Now what helps is to shift this force to somewhere here, because when it is like that, you can't really do an arrow that is going into the object. You want an arrow that is moving away from the object to suggest that it's pulling the object, okay? So just remember that the force will have to be shifted in a way, okay? So let's do it instead of talking about it. So we've got our object. We can see that this force here is going to be acting in this direction. Okay, that's the applied force. And then what do we have? We've got the normal force directed straight up. Doesn't really matter that its proportion is small. Okay, maybe let's make it sizable. We have enough space. The normal force is like that, and then the weight is straight down. Oh, it can't really not be a straight line here. So we've got our gravitational force here, and then we know that we're going to have our frictional force. Okay, so these are the forces that we need to capture. So you're getting a mark for that. This is basically the applied force. And then, yeah, that is how you score those 4 marks. Let's move. 2.1.3. Now we are told here, a constant frictional force of 2 newtons acts between the surface and the crate. Now calculate the magnitude. So we want the magnitude here of the normal force, okay, on the crate. I don't know why it's refusing to do the things that must be done, okay? So we want the normal force. Now the normal force is part of the horizontal forces. Remember, this one may mislead you a bit because it's hiding those components. So you may want to look here. What are the vertical forces? Because the normal force is a vertical force. So of the vertical forces, it's the normal force is the perpendicular component of our applied force and the gravitational force. So we can put it down here so that we know we have something to work with. Okay, so we know that there's 2 forces directed down. There's the weight, and we've got this perpendicular component of the other force. Okay, but it doesn't look like it's doing the things. Okay, so it doesn't matter which one is bigger than the other. I'm not really interested. So this is going to be the Fy. This is the Fg. And then, of course, these together are being opposed by the normal force, which should be exactly equal to the sum of the 2. So once you do your diagram like that, a force diagram, it helps you a lot, because we can say now from Newton's second law, the Fs equals ma. Okay, that's what we know, which implies what? Now we're going to make the normal force positive minus the sum of these 2, which is going to be Fy plus Fg is going to give us ma, isn't it? Great. And then now we can say, therefore, our normal force is going to be ma. Now, once you transpose the pair, they all become positive. So it's going to be Fy plus Fg, okay? Now we can substitute. This was 4 kilograms. There's no movement in the vertical position, so the acceleration is 0. Plus Fy. Remember, you look at this triangle here. If you want Fy, it is opposite this angle. So you can say sine 30 degrees is going to be Fy over F, okay? And then you just cross multiply. I don't want you to cram this. I know you can know it from memory. So this is going to be 10 sine 30 degrees, okay? Plus Fg is basically 4 times 9,8, okay? That's easy. So let's kill the bull. Let's kill the bull. So we've got here 10 into sine 30, which is basically a half, honestly. Don't know why I'm even doing this. Plus, and then 4 into 9,8. So guys, I'm getting a 44,2 newtons. And remember, the normal force is directed up, but we were asked for the magnitude. So no worries about direction, but because it's a vector, we just want to make a habit of doing the right thing. Mentioning the direction won't deduct marks from you, but if they just said calculate the normal force, now you have to think about this. So you want this to be second nature, so that you don't have to fish for it in the dark, okay? You always get a mark for the formula. I mean, the best one is here, because that is just general. It's not significant in my opinion. This is best. But either way, to protect you from losing marks if you wrote this incorrectly, then it's just for your protection, honestly. It's not really a must. Okay, then correct substitution, and then the answer. How many marks are we scoring there? 3 marks, yes. So it's a standard 3-mark question. So easy. 2.1.4. Next question says we want the acceleration of our crate, okay? So acceleration, because we're moving this to the right, so it's horizontal motion now. So let's look at the horizontal forces, because the vertical forces pretty much cancel each other out. So they are no longer the issue. But now our applied force is acting through the Fx. Okay, it's acting through its horizontal component, because its vertical component got chowed by the normal force. Okay, this is now Fk. So there's two horizontal forces there, is the Fx and the Fk. And we can see this one is the dominant one. So again, from Newton's second law of motion, F res equals ma. What are you doing? This implies, now we know that we're going to make this one dominant, Fx minus Fk equals ma. Alright, now let's go for it. What is Fx? Again, you're looking at this diagram. Fx is on the adjacent side, isn't it? So if it's on the adjacent, you say cos 30 degrees is going to be Fx divided by applied force. You just cross multiply the force, you define your Fx. Please don't cram it, because certain diagrams are not going to always say cos or sine. You have to look at exactly the position of the force or the component. So now this is going to be 10 cos 30 degrees minus, they told us that it is 2 newtons, which is going to be equal to 4. 4 multiplied by a is just 4a. Alright, so we can already see here that therefore our acceleration is going to be this 10 cos 30 degrees minus 2 newtons divided by 4. Okay, so let's do the calculation. It's pretty simple. So we've got here 10 we've got 10 into cos 30 minus 2 divided by 4. So what I'm getting here, remember now we were told minimum of 2, so we're going to keep it to 2 decimal places, and in fact I should keep it to minimum of 2. If you show up with 1, you are dead. So this is 1,67 meters per second. Remember, acceleration is per second squared. But now in which direction? To the right, isn't it? Yes, because remember it's a vector quantity. So you always think about it. That horizontal component of this force was directed to the right, so it makes sense. Okay, easy. Now you're not going to get a mark for the same formula again, because you did in the previous. So what matters is the definition of our vertical component, horizontal component, and then the general substitution, and then the answer. Easy. Oh, they're giving you 4 marks. Wow. What else is significant? Now I'm trying to think. Why so many marks for this thing? Okay, maybe we can say, okay, you're getting a mark for the formula anyways, it's fine. But it's not necessary when you've been using, this is a sub-question of the same question, so you can't get marks for the formula each time. Doesn't make sense. But anyway, let's move on. Now, if the angle of the 10 Newton force is reduced, okay, how will this affect the magnitude? Choose from increases, decreases, remains the same. How will it affect the magnitude of the normal force? Do you see that this question is really similar to the first state one? So let's look 2.1.5. What do we know? The normal force is one of the vertical. You don't want to draw this multiple times. If you have it, you work with it. And then you're like, okay, the normal force is equal to the vertical component plus Fg. Now, we know that the normal force from above we found out that it's basically Fy plus Fg. Okay, this is what determines our normal force. Now we want to use this to decide what will happen to the normal force when that angle decreases. Now what in this equation is related to the decreasing of that angle is this friend right here. Now how do you define this friend? This friend is defined as, let's look at Fy is equal to F. Okay, let's just write it as it is. It is still 10. So it's 10 sine theta. Just say theta now. Measure it in general. Okay, in general, this is the 10 is for the size of the force times sine of theta. Now, if you're decreasing theta, the sine decreases, meaning this product becomes smaller. And as a result, this one is going to become smaller. So in effect, what are we doing here? We are reducing our... So we're basically reducing our Fy. As a result, what happens to the normal force? Because Fg stays the same. If we're reducing this part and parcel of this equation, it means this result becomes smaller than initially. So the normal force will decrease. It decreases. Okay? And your tools are these two that explain what is going on. Okay? You always need some sort of equations to make sense of this. Otherwise, it becomes a little bit difficult to figure out. Okay, let's look at 2.1.6. It says, what about the acceleration? Now, the acceleration of this object, okay, explain the answer even. Okay, this time you're going to have to say something about your explanation. Now, in terms of the acceleration, we know that the acceleration in general, just think about it in general, in this diagram, because we already have these two horizontal forces, acceleration is basically the resultant force, which is going to be Fx minus our Fk all over mass, isn't it? Don't worry about other things. Just think about it in general. This is the equation that we can use in this diagram to actually explore the acceleration. Okay. Okay, I don't know what I'm doing. All right. So now, what in this setup changes when the angle changes? It is this guy right here. Okay, so how do we define that guy? Fx is basically equal to 10 cos theta. We're just going to talk about it in general. Of course, pay attention to the diagram at hand before you make any comparisons. Now, let's look at this. What happens when we decrease the angle? Remember, as you decrease the angle, this guy entirely becomes bigger. With cos, it's a different story. When you decrease the angle, the cos increases. I don't know if I'm making sense. Let's just put it to the test. Let's say cos of 5. What is cos of 5? Cos of 5 is 0.99, which is around 1. Let's see what is cos of 2. Cos of 2 is 9, but you can see it's much bigger. Let's say cos of 1. Cos of 1 is more or less, but I mean, if you're looking at it, let's look at in terms of 30 versus 20. Cos of 30 is root 3 over 2, right? Which is basically 0.86, which is 0.9. And then let's see cos of 20. Cos of 20 is 0.9. 0.94, but the other one was 0.8, so this one becomes smaller, bigger, sorry. I don't know if I'm making sense, because that was 0.8, this one becomes 0.9. So in a way, we know that by dropping theta, actually this guy as a whole increases. Okay? If this guy increases, that product increases, and it means our force increases. I don't know, I wish I was able to swing this force down, because you will see that when you swing this force down, it will swing in such a direction that it goes like that. Perhaps it could be somewhere here to get the same value of that force. And then you can see that this is a smaller angle. So what do you see here? The vertical component is shorter than the initial, but do you see the horizontal component becomes extended? So there's plenty of ways you want to look at this to try and make sense of the situation. But yeah, either way, you can use a calculation. This calculation can be very misleading, because if you don't know what's happening to the course, you start to feel like you're bending, but yeah, you're not exactly bending. So now let's look at this. If we're decreasing the angle, we're effectively increasing cos theta, then this product becomes bigger, effectively increasing our horizontal force. So now this means here we are essentially increasing fx. Remember, fx initially was smaller, so the result was small, but now this is bigger, and we're subtracting the same small amount. So in a way, we know that the numerator increases. If the numerator increases, what happens? Acceleration increases. Great. So we know that this increases. Okay, great stuff. But now we need to explain. We can say by decreasing the angle of the 10 Newton force, the horizontal component, let's just say its horizontal component, increases, essentially resulting to an increase of the resultant force, okay, in the horizontal direction. Therefore, acceleration hayibo kuvele kuthini na kodwa nkosi yami wena hayi andazi. Therefore, acceleration increases since A is directly proportional to F res. Remember that. Sometimes you want to add some equations because they said etc., whatever you can use. So when you look at those marks, those are not marks you want to throw away. You just want to give your best, okay? First of all, you're getting a mark for choosing that. And then now to describe that by decreasing the angle of the 10 Newton, its horizontal component increases. This is important, okay? Resulting in an increase in the resultant force, okay? Great. That whole statement or that whole phrase or paragraph or passage is a mark. Now you can say, therefore, acceleration increases because it is directly proportional to the resultant force. That on its own is the third mark. So yeah, you know how to get marks, guys. I don't want to overly indulge here. Let's get to this one. Now we're told you state Newton's universal gravitation in words, okay? Okay, we know that this one says every particle in the universe attracts, okay, maybe let's just say a particle. Yeah, but I think it's fine. Every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely, my inversely is not good, and inversely proportional, okay, to the square of the distance between their centers, okay, or you can just say between them, it doesn't really matter. All right, every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses. These are very key areas. And inversely proportional to the square of the distance between their centers or between them. So that's how we sort out Newton's universal law of gravitation. Easy stuff, textbook material. Now calculate the acceleration due to gravity for an object on the surface of the Earth. Remember, there is a formula in your formula sheet that says G is equal to the big G, the big M over the big R squared, because it just says the mass of the Earth divided by the radius of the Earth. Now this one is 6,67 times 10 to the minus 11 into, I don't remember the mass of the Earth. Is it 5,98, something like that, times 10 to the exponent 22? But let's have a look. I have to open my phone because I forgot to copy those formulae. So this one is the mass of the Earth is what? Yes, 5,98 times 10 to the 24. Wow. Still have a bit of memory. Did I say 24 or 22? Don't remember. The radius of the Earth is 6,38 times 10 to the exponent 6. And then we are squaring it. Alright guys, so here the key is that if you do a wrong calculation, we'll see that you're not going to get 9,8, isn't it? Yeah, 6,67 times 10 to the exponent minus 11 into 5,98 times 10 to the exponent 24 divide by 6,38 times 10 to the exponent 6, and then we're squaring it. Let's find the answer. So I'm getting 9,8 0 meters per second squared. Okay, so that's that. Easy stuff, no need to panic here. Formula, substitution, answer. And by the way, the direction of the acceleration is very controversial at this point. If we're saying due to gravity is towards the center of the Earth, I guess that is the most important direction you cannot forget in a vector. So we can say towards center of Earth. Okay, of course here they just said calculate acceleration due to gravity, so you need to include direction because this is a vector. So these things, guys, are critical. So I would give you 4 marks for this one because this deserves a mark. All right, so guys, we've done question 2 in just an hour. So let's quickly rush through this one so that we can save up some time. Now, question 3 says a car of mass 1,5 kgs is stationary. Once you're saying stationary, VI is equal to 0 here. Okay, at a traffic light. It is hit from behind, okay, by a minibus of mass of 2000 kgs, traveling at a speed of 20 meters per second. That is its initial velocity. All right, now you can see here these two guys, this is a polo, right, and this is a taxi. These two people are the craziest on the road, so they deserve each other, so it's good that they hit each other. We are so tired of them on the road. We just wish they could just be removed from our roads. Anyway, we can't live without them because these become transports for the general public. These are the most affordable cars for anyone who is earning a bit of salary. So at the end of the day, it's really unfair to pass such comments. All right, immediately after the collision, the car moves forward, okay, at 12 meters per second. Okay, now that is the final velocity of the car. All right, easy stuff. So we know that we're doing momentum here, so they're just making the luxury of drawing these, so not a problem. State the law of conservation of linear momentum. Easy one. We can say total linear momentum in a closed system is constant, okay, or remains constant, or is conserved, or remains conserved. This is the easiest, guys. What is important is to state that there is a closed system, and the rest is history. So easy 2 marks here. Calculate the speed of the minibus immediately after the collision. Easy, we're using conservation of linear momentum. So we know that total momentum before is equal to the total linear momentum after the collision, okay? Now what do we do here? The mass of the minibus, you can just say MBVIB plus MC, which is the car, VIC is going to be equal to MBV final B plus MCV final C. All right, so I don't know why they chose V for everything. U and V were good, U being initial and V being final. It really stops this nonsensical situation here of just having too many subscripts. It's ridiculous. I'm actually against it, but who am I by the name Zamabuhle Makamba to say anything? I must just shut up before someone does it for me. What was the weight of the minibus? It was 2000 kgs into the initial was 12, right? Plus this one is 1500 into 0, because the initial, we were told it's stationary at the traffic light. Now this one is going to be 2000 VFB, because that's what we want, plus 1500 into now 12. Of course, guys, make a habit that you're choosing to the We're choosing to the west as positive. You see the dominant direction of motion. Just choose it as positive and that's going to okay, so that you don't make a mistake of issues here. Now we can already tell here that, okay, this implies that now, in fact, I don't want to be wasting any more time. Let's just do the final gymnastics. Say therefore, V final of the bus is going to be 2000 into 12. Then we're going to subtract 1500 into 12. All of that over 2 squared. Then let's see what is that. So we've got 2 squared into 12 minus 1.5. So here this one is 1 squared to 35 into 12. Yeah, wait, that was a 40 thoughts again. God, father. So this one gives me 3 meters per second, and then of course it's positive, it's to the west as well. So velocity I always treat with respect, although I may have been asked just to calculate the speed. I mean, this is a speed, so I mean speed is a scalar quantity, so this is not necessary. If you start putting a direction on a scalar quantity, it's a controversial one. In fact, I would want to punish you if someone gives me a shot. So let's see, guys, what is the story here? Formula, but the biggest is this stage here. But if you write it wrong, at least you have a protection there. 2 correct substitution in general and an answer. But now, what is the 4th mark? I think it's noting that the initial velocity of our car was 0 because it wasn't clearly stated. So is 4 marks. Now I told you the driver of the minibus is not wearing a seat belt. Okay, not a problem. Now describe the motion that the driver undergoes immediately after the collision. All right, so this guy will undergo, we can just say the driver Now, what are we talking about? Oh, the driver of the minibus. Now, remember, the driver of the minibus, remember, is this guy sitting right here, making all the noise. Okay, maybe the other way around. So it's that guy there. So what happens when he hits here, he's going to be ejected in that direction. It's going to be moving towards the windscreen. Okay, so the driver will be pushed forward to the windscreen. Okay, that is how it's going to move. It's going to be moved towards the windscreen, or it may even hit the steering wheel and sustain chest injuries. So this one can give him a commotio cordis, blunt chest trauma, and the heart starts doing its own things. We call it commotio cordis, and that can kill. That's what kills a lot of people. That's why you want to wear a seatbelt, to protect yourself from this impulse when you're hitting the steering wheel. Or he may even, have his neck flexed forward, and then he hits the windscreen and sustains some injuries to the face there. But that's how it's going to be. The driver will be pushed forward towards the windscreen or steering wheel. You're just being silly now, okay? You're saying too much. There's no need. And then it says, now name the law. It is the law, okay? Name the law of physics which can be used to explain your answer about the motion of the driver. Remember, the driver was traveling in that direction, and this guy attempts to stop this one. But now, because of the law of inertia, The law of inertia is going to say, I want to maintain my speed. That's why he will be like pushed forward a bit. So that is the law of inertia. Or you can say Newton's first law. Let's just say Newton's first law of motion. Okay, it says a body will remain at rest or continue in its uniform velocity unless acted upon by an external resultant force. So that is that. So Newton 1, or you can say law of inertia, because this characteristic is much more elaborate than just saying Newton's first law, but either way it is one and the same thing. All right guys, so you're getting a mark there and you smile. Okay, let's move on guys, I'm wasting time here. I want to finish this business quickly. All right, now we're given here the following velocity time graph is obtained for an object in free fall. Free fall means only gravitational force is acting. Then when we're saying neglect any air resistance, we are also creating a closed system, meaning no other forces are involved. But I think already free fall just captures that in general. So this is just tautology to repeat what you're already inferring, because this inference already tells us only the force of gravity. So this is essentially more like a closed system already. So we're already ignoring air resistance when you're saying free fall, isn't it? Exactly. So why are you repeating yourselves? I don't know. Anyway, now what is most important guys, the area under the velocity versus time graph always gives displacement, or you guys call it position nowadays, okay? Or you can say, if this is a speed time graph, you can say distance. But we know that this is not technically just distance, it's displacement. So I'll put an asterisk to that one. And then of course, what about the gradient? The gradient here, we know that it represents acceleration. Usually we use letter M for gradient in maths. So the gradient represents G, which is acceleration, all right? So these are some of the things you want to make sure you refresh so that you kick this thing when you have to deal with it. Is there anything else? There's nothing more here. So these are some of the things you want to consider as you're working with a velocity time graph. And then now we can see that, okay, the initial velocity at time zero, remember anything that is time zero is initial. The initial velocity is negative, and then the final velocity is positive. This is the final because this is where we end this. Even though we're continuing, we don't care, we'll regard this as the end. Okay, great stuff. So we know that this this is just G. That is G. Okay, so if you ever have to do any calculations, you know that that is G. And then of course the area under the velocity time graph gives us the displacement, which is also seen on this side. Okay, easy stuff. Now what we see here, okay, is that this velocity comes from a negative but goes to zero. Okay, so literally this you would say is an increase, and then it continues increasing. So but when it increases from a negative to zero, when it increases from negative to zero, what does that mean? It means our object must have been projected from a particular height. You know, it must have been thrown upward, reached some maximum height, and then went down to the ground. Because you can see here that the level of this object, you see from zero, this side is disproportionately bigger than this side. So this already tells us that this went from already a height above the ground, went to maximum height. This is where velocity became 0 meters per second. This is at this point right here. Now what time did it take to reach maximum height, it took 0.25 seconds. It will take the same amount of time to return to the same level. Okay, but now the velocity is directed opposite. It will be the same size but in the opposite direction. Okay, so if we were to look at this thing in this side, it would be somewhere here if I'm just making an approximation. Okay, maybe it's too small here. Maybe it would be somewhere here. So okay, and then you would know that across, if you're reading, this would be the same distance from 0 to the positive version of it. So you can see that that area is part of this, and there's still more, so it means it went further down. So this is something like a scenario like this. Say this is the top of a building. Okay, there's a window there. Okay guys, I overly indulged. Let's just keep moving. Now it says explain what is meant by the term free fall. Okay, easy textbook work. Oh, by the way, what can we notice here is that if this is being projected upward and it's negative, it means we chose up as negative and then down as positive. Just a moment. Okay guys, let's keep moving. So essentially this is our sketch of what is likely happening in this diagram. So this is more of a position time graph versus our velocity time graph. Usually this is what makes more sense than sometimes this would. Anyway, let's decide. Well, let's define free fall. A free fall is defined as motion in which only the gravitational force is, don't be like that, is acting. Okay, so it's a motion in which only the gravitational force is acting. Easy 2 marks, nothing major. 4.2, let's just move guys. I'm too relaxed here. Use the graph above. You see, use what? The graph above to describe fully the motion of the object. So you can see that if we have done this job, this technique actually fits the whole thing right here. Of course, this would be 0.5 seconds, isn't it? So what we can do here, we can say, well, this is an object that was projected upwards from a height above the ground. All right, yeah, I think that is what we can say. And then of course I said fully, so we can say an object is projected upwards from a height above the ground. All right, and then undergoes free fall until, okay, maybe let's do that rightly, until it returns, or until it hits, let's just say until it hits the ground. Remember, we don't know the exact situation, but this fits into the picture that we are given. So you always are going to make an approximate, thingy. And then we can say down. You can just say downward. Maybe let's just start by saying upward. Maybe it's more sensible. We can say upward motion is regarded as negative direction. Okay, the upward motion is taken for a negative direction. That is the full explanation. I think it's 2 marks for that, and to state exactly how the direction yani ayiwena man sinhlanyisa wena man sikanhlanisa wena man iyantina jwala. All right, so that is the story, guys. So always make sure you are as comprehensive, once they say fully. You're not going to be taking shortcuts. Okay, so these are some of the things that are important. Okay, now let's do some calculations, which is our favorite business. Now it says calculate the initial velocity of the object. So let's just look at this portion of our graph. This portion here, basically it gives us all that we need, because we know the gradient, we know what g is, we know the time it took to get there, and we know that the velocity is 0. So we need all of those things. So we can say here 4.3. We can say now at time t0 to time to 0.25 seconds. Okay, usually it helps sometimes to direct someone what you are doing, because if you just show up with numbers, it doesn't make sense. It's like geometry, you know. Then we know that, okay, we can say now here v final is equal to the initial velocity plus g delta t, the simplest of equations, isn't it? We know that the final velocity is 0 there, okay, and then the initial velocity is what we want, plus here g is basically 9.8. Why is over 9.8 into 0.25, because that's the time, right? We can say therefore our vi is basically that transposed. So it's going to be 9.8 into 0.25. So this basically is 2.45 meters per second upward, okay? Which we can just write it here, 2.45 meters per second upward. Remember, they said velocity. They didn't really state what you must be doing, okay? So this is easy, guys. Always map your working area so that nobody is confused. So easy, 3 marks here, nothing big. So formula, substitution, and answer. But remember, you don't get a full mark for the answer if you did not include direction, because they didn't specify what is this, okay? So you must, but again, if you just left it at minus 2.45, it's still okay, because that negative actually makes up for the direction. As you could see that from the description, we said upward is taken as negative, so that already makes sense right there. So you may be forgiven if you forget. Now calculate the final velocity of the object. So we really want the velocity here. So we want to know what is that, which is more likely the velocity with which it hits the ground. Again, we know the gradient is still g. We know the time is 4 seconds. Now we know the initial velocity. Unfortunately, we just have to use that at this point. So again, we're going to say the final velocity is initial velocity plus g delta t. I hate this delta business now, which implies that we want our final velocity, the initial velocity. Remember, when you substitute it, it's going to be minus 2.45, because we took up as negative, plus 9.8 into 4. Okay, so let's quickly answer the question. So it's minus 2,45 plus 9,8 into 4. So what we're getting here is 36,75 meters per second. But now this one comes out positive, so it's downward. Okay, maybe let's not write too many words. It's downwards. We have to interpret the direction because it didn't just say magnitude. Again, here, I mean, it's not a sub-question of this one, so it's correct to give a mark and a mark and a mark. So how many marks there? 3 marks, easy. Now we're told here, draw the position time sketch graph for the entire motion of the object, and then take the starting position as 0 position. Okay, indicate all relevant times on the graph. Okay, that we can do pretty easily. So this is 4.5. So let's try and get this one. Okay, by the way, we start by naming. What is this? This is the position time graph of object. Okay, remember they already dictated the direction here, so you don't forget to correct for that. So remember, a position time graph is always going to be like a velocity time graph. It has both negative and positive components because that is the story. That is the story. It doesn't look vertical here when. All right. Now here we know that this is the time in seconds. And then now this is going to be position in meters. And then this is the 0 mark, right? Right. Okay, this can be going forward like that. And then now, what do we do, guys? Remember, we chose upward as negative. So it means our drawing is going to be doing stuff like this. It's a parabola that swings like so. Gets to maximum height and then goes to the final position. Why is it not doing the things now? I win. So it does something like this. All right. Yeah, it's not really doing the things that must be done, but it's something like it. Let's try one more time. So it's doing stuff like this. Okay, I think it's much better. It is very better, so we can just push it to the origin there. And then we can tell that, okay, this would be the final displacement right there. And then this final displacement, we know that we reached it at time at that time. So let's just sort it out, guys. We don't want to lose too much time. So we want to break it up into 4. And then now remember, the relevant time that we know we've been given was basically the time to maximum height, isn't it? Yes. The time to maximum height was given to us as 0.25 seconds. But remember, the time it takes to reach maximum height is going to be the time it takes to come back to the same position. So 0.25 by 2 is just 0.5, and then 4. So those are the times that are relevant to show. And then, of course, considering the direction that was dictated, we didn't choose it, they chose it for us. So this is where we are. Okay, guys, that's easy. Of course, you're getting a mark for your times. How many marks was this thing anyway? 2 marks. Of course, the keywords I'm sure is these ones, and then the shape of the graph. But that is not to be forgotten because time symmetry somewhat dictates it. All right, easy stuff, guys. Let's move on to organic chemistry and try to move as fast as possible so that we can hit the 2-hour mark that we are chasing. All right, question 5 says the letters A to E in the table below represent 5 organic compounds. Okay, if you're looking at this one, you can see that C double bond linked to the hydrophobic chain with an O. So once you see a link to something like this with an O, you know that this is an ester. Okay, of course, when you name the ester, you always look at the hydrophobic. How do you know which one is the hydrophobic? Is this the end or is this the end? The answer is the hydrophobic end is the one that faces the oxygen. Okay, always when you want to decide which one is the hydrophobic end, is always the part that is facing the oxygen, the single bond to oxygen. Okay, not the double bonded oxygen. And then of course the esteric part or the carboxylic part is the part that faces the carbonyl group that you see there. Okay, enough explanations there. Now we've got here 2-methyl butanoic acid. 2-methyl. So once you see 2-methyl, it's a branched carboxylic acid because this OIC is a carboxylic acid. So you can just say it's a branched carboxylic acid. Easy stuff. And then we've got pentane 2-ol. Once you see any number other than 1 before the OL, it means we have a primary, no, liar. We've got a secondary alcohol. Okay, how would you know if it is a tertiary alcohol? If you've got a number other than 1 before the OL, and then the side branches, and one of the side branches coincides with this number, then that becomes a tertiary alcohol. All right. Now 2,2 trimethyl hexane. So this is just a branched alkane. And you know the significance of this. A branched alkane compared to a straight chain alkane of the same molecular mass, they will actually have different boiling points. All right. That is the essence of this. And then also with the carboxylic acid, if it is branched compared to its straight chain counterpart, meaning its isomer, they will have different boiling points as a result. Okay, now we've got here C4H8. 4 times 2 is 8. So this follows CnH2n, making it an alkene. Right, you're just doing a bit of a walk so that you can, do the things that must be done. Now use the above table to answer the following questions. For compound A, okay, we can see that this is the ester. Name of the homologous series to which it belongs. Already we answered it. So 5.1.1, we know that these are esters. Working away with the mark. 5.1.2, it's IUPAC name. Sometimes you may be surprised and asked, what does IUPAC stands for? So this is International Union of Pure and Applied Chemistry, okay? Don't be beaten by that name. Otherwise, we want the IUPAC name. So remember, when you are giving the IUPAC name of an ester, always name the hydrophobic end first. And as we said, the hydrophobic end is actually just forward of the oxygen, or it's just facing the oxygen. That doesn't have a double bond to a carbon, okay? So that is 1, 2, 3. So it's a propyl. So it's an alkyl group. So this is propyl. Now name the carboxylate end. which is going to be 1, 2, 3, 4. This is now butanoate. Propyl butanoate. Okay, you're getting 2 marks for each of those thingies there. So 5.1.3, it says now name of the homologous series to which its functional isomer belongs. Remember, esters have functional isomers in carboxylic acids. So this is carboxylic acids. All right, because if you're taking a molecule of the same molecular mass in the carboxylic acids, it will exactly be the same molecular mass as would be the counterpart in the esters. So those are isomers of each other, functional in the sense that they belong to different homologous series. Okay, now question is, what is the functional group? Functional group is defined as a bond, right? Because remember, with alkenes, what is functional for alkenes is the type of bond between the carbons in the chain, isn't it? It can be a double bond, a triple bond, essentially. It can be an atom. Okay, think of haloalkanes. You have a halide atom there, so it can be an atom or group of atoms. Think of esters. Think of carboxylic acids, COOH. That's like 3 atoms they put together. So it can be a group of atoms that determines the physical and chemical properties of a group of organic compounds. Okay, so we're talking about organic compounds here. So remember, this can be a bond, as in double bond or triple bond in the carbon chain, or it can be an atom as a substituent like in haloalkanes, or a group of atoms like in alcohols or carboxylic acids. Those are substituents, by the way, and mixed a bit. So there's a few variations, but what is important about this, it imparts the physical, like boiling points, vapor pressures and stuff, type of intermolecular forces, and the chemical properties. Is it polar or non-polar, depending on those substituents that are dominant or predominant. So basically, this is what a functional group is. In fact, maybe I should say determines the predominant. I think it's better to say that, because there are some other things that are there. Determines the predominant. Okay, my predominant is not going to fit. Okay, I don't know what is happening there, but whatever is happening. So that is predominant physical and chemical properties of a group of organic compounds. So it's a very nice question. Please don't be chowed by that thing. It is not too difficult. Okay, write down the name of the functional group of compound B. Now compound B is carboxylic acids. So now we want the name of its functional group. Now the functional group of carboxylic acids is what we call the carboxyl. Carboxyl group, okay, or the carboxyl ion. Now draw the structural formula of the functional group of compound E. Compound E is an alkene. Now remember, in alkenes, you take the simplest alkene, which is ethene, right? But now you're not going to focus on ethene per se, but all you're focusing on is that with alkenes, Remember, the horizontal lines represent a carbon chain. Vertical lines may talk about a substituent versus a hydrogen. So remember, that is different from just saying this is ethene. It's not necessarily ethene, but we're just taking the simplest, but we're suggesting that the chain could be even longer. So horizontal lines here, it has to be horizontal. If you show it at an angle, you are telling us that this is a hydrogen or a substituent, and that is not acceptable. So it has to be horizontal versus vertical. So that is just the key point in drawing a functional group, where the functional group is essentially a type of a bond in the carbon chain. Okay, now define structural isomers. Okay, now structural isomers are defined as molecules, let's just say compounds instead of molecules to avoid tautology. It's compounds with the same the same molecular formula but different structural even that structural is wrong. Structural formula. Just leave it at formula. You can just structural arrangement of atoms, which is essentially the formula. So easy, 2 marks there. Nothing big. Now consider compound C. Now let's look at compound C. It is pentane 2-ol, so it's the secondary alcohol. Okay. It says now classify compound C as primary, secondary, or tertiary. We know that that is the story. So 5.6.1, it is a secondary alcohol. All right, give a reason for its answer. It's because the carbon bearing the OH minus ion is bonded to 2 other carbons. The reason we know that it's because it is a number. There is a number before the OL, so it tells us the position of the OH in the carbon chain. So that is a secondary carbon if there is no side branch to that parent chain, which coincides with the same number of the carbon position. So now this becomes a secondary alcohol, so that's what we know. Okay, great, that's easy. So you're getting a mark for each of your attempt A. Now it says draw the structural formula of the positional isomer of compound C. Okay, so we want the positional isomer of compound C. Remember, compound C is 1, 2, 3, 4, 5. That was pentane 2-ol, isn't it? Yes. So remember, pentane 2-ol, it means our OH group was here. Okay? And then with hydrogens there, hydrogens. Remember, these are saturated molecules. Okay? So this is its name because, we're prioritizing the OH group because the OH group is in the second carbon. So when we start naming them, it's carbon 1, 2, 3, 4, 5. Okay? Now the positional isomer is going to be shifting this OH to somewhere either than the second carbon. And of course, there can only be 2 isomers here. It can be either here or here. Otherwise, if it is here, it's on the second carbon because we'll always prioritize the shortest distance to the functional group. So it can either be here or there. Otherwise, the name will always be either pentane 2-ol or pentane 3O. So basically now the functional isomer here is C. Yeah. So basically we are saying, all right, okay, we're going to just we switch the OH around. So the OH must come here and the hydrogen must go there, because this is the third carbon and it's allowed. It's just in the middle. But if you moved this OH here, it becomes the same molecule, so you lose marks, okay? Great. But what other positional isomer could you do? Actually, there's two. I was correct when I said two. It's either here or in the first carbon. So if you can put this OH in the first carbon, it's definitely a positional isomer. All right, so let me think about it. But now that becomes a primary alcohol, but definitely it's a positional isomer, even though it's a primary now, no longer secondary. But for the sake of consistency, I will choose a position that still makes this one a secondary alcohol, okay? Because I think the type of alcohol is also pretty important, because when you're putting it here, it becomes a primary alcohol. Now, I'm not sure if we're going to be happy about that, but actually, in essence, by definition, it is a positional isomer. But I would rather we keep to the same category, secondary alcohols, and that is okay. But you would not be punished if you put the OH either in the first carbon or the last carbon, because it's one and the same thing. Okay, so let's look at now compound D is a hydrocarbon. Okay, we saw that compound D is basically a branched alkane. Yes, that's true. Now it says define the term hydrocarbon. Again, textbook work. Now we know that a hydrocarbon is defined as a compound that contains only hydrogen and carbon atoms. I'm panicking, guys, because time is essentially escaping me and I'm not moving. Okay, easy here. It's only hydrogens and carbon atoms. That's it. Easy, 2 marks. Draw the structural formula for compound D. Okay, now compound D is 2,2,4 trimethyl hexane. So the parent chain is hexane, so 6 carbons. So 5.7.2. We've got 1, 2, 3, 4, 5, 6. Okay, and then now we are saying it's a hexane. So here there's no functional group because everything is single bond. So what matters now is the side chains. They take precedence. They are the next in line. If you don't have the president, the deputy takes over. So side chains or substituents are deputies of the functional group. Here the functional group is flexible. So now we're saying there's 2,2,4. So this is 1, 2, 3, 4. Okay, let's see, it's 2,2,4 trimethyl. So these are methyl groups. So we're saying first branch goes there, and then of course you do your hydrogens, and then here it's going to be another methyl group because it's 2,2, and then this one is a methyl group as well on the 4th carbon, and then of course we're just going to have a hydrogen there, hydrogen, hydrogen. All right, so as you can see, we prioritize now as many, not just one, because remember, you could have decided you want to come this side, but do you see you are much closer to as many side branches when you're coming from this end than when you're coming from this end. So this is why this is correct. So IUPAC naming is saying that. So this is what we were supposed to do. And that's how we get those marks. I guess is the parent chain, which is 6 carbons, and then essentially 2 marks for the position. I mean, this position of these 2 substituents and the position of the third. So that's how the marks are distributed. Did we answer all questions? I believe so. Okay, guys, so we are good. Why didn't they ask anything about compound E? Okay, they did here. Not a problem. So let's move on. We are almost out of time, so let's do question 6 quickly. Question 6 says, an investigation was conducted to determine the boiling points of straight chain organic compounds X, Y, and Z from 3 different homologous series. So this means they're not belonging to the same group, okay? The table below reflects the results obtained. So we can see here that the boiling point is negative. The boiling point here is essentially positive, okay? And that one is more positive. If we can just use signs to try and, elaborate what is going on. So let's leave it at that anyway. But you can see this one is small, so it's the lowest. This is high. This is highest. Sorry. So these are some of the things you just, try to play with your information. Just a little bit, not too much. So the question says now, okay, just a moment. Okay, guys, I'm back. I'm sorry for the noise. I just had to clear my throat a bit by drinking some water. I get a bit throaty when I talk too much. So as I was saying, please be in a position to play a little bit with your table so that you can, formulate something. So define the term boiling point. That one is textbook work again that you already know. So let's find out, what can we say about boiling point? The boiling point is defined as a temperature is a temperature where is a temperature at which the vapor pressure is equal to the atmospheric pressure. Okay? For a given substance. Okay? It has to be a particular substance, isn't it? Not just any. But anyway, that's just being overly elaborate. It's as simple as that. Atmospheric pressure equals vapor pressure for a given substance, and that is that. 6.2, it says now, which compound X, Y, or Z will have the lowest vapor pressure at room temperature, and give a reason. Now remember, the one with the lowest vapor pressure, it means the molecules are held together. A gaseous phase is what forms the vapor, isn't it? Because this is when the particles or the molecules are sparse or far apart. So now they are closer together in the one with the highest boiling point, because the one with the highest boiling point, it means it takes a lot more energy to separate molecules into gas particles so that they can form a vapor. So the one with the highest boiling point is the one with the lowest vapor pressure at room temperature. So we can say Z. Z for Zama. All right. Anyway, so that is the story. And then now the reason is that it has the highest boiling point. Of course, if you were to ask how you explain this, you will know how to explain it. These things. So 6.3. Which compound XYZ is a gas at room temperature? Remember, at room temperature, it means it's already gone past its boiling point, meaning molecules have been separated into gas almost entirely. Now, when you look at the boiling point, this one, this guy right here, boils at already minus. By the time you're at room temperature, you're way beyond the boiling point. So that means almost entirely this molecule is essentially a gas rather than it would be a solid or a liquid. Okay, so that's X. So it's X, okay, because it has the lowest boiling point, which is already, it boils before room temperature. So that's basically the intention. So if it boils before room temperature, it means by the time you hit room temperature, you're way above the boiling point. So that temperature is too high to allow any portion of that molecule to even be a solid or to be a liquid. So it's no longer condensed, it's like separated into molecules, like particles, as in a vapor. Okay, so they didn't ask for an explanation, we'll leave it at that. Okay, 6.4. What does 6.4 want? It says, now write an investigative question for the above investigation. Okay, we can see here that we want to know what is the influence of a functional group to the boiling point. So we can say here, how does the functional group influence the boiling point of a substance? We can say, how does the functional group influence the boiling point of a given substance? Okay, that's it. I mean, you can phrase it in any way, make sure it makes sense. Key is, does a functional group impart a particular phenotype in a particular substance in terms of its physical properties? Now this is when you're trying to be more advanced and silly in science. Okay, we don't need to be very silly, we need to be straight and to be yes. Okay, give a reason why all three compounds give a reason why all three compounds used in the investigations are straight chain. Why must they all be straight chain? Remember, we're just using that as control. Okay, it's a bit vague though, because we don't know that as straight chain, are they of equal length? Because I would rather they say they are straight chain, but those chains are of equal carbon length. All right, they're of equal chain length, so to speak. So I'm not too sure. It's a bit vague, but yeah, whatever you had in mind, guys, we got it. I think we're going to say it's just for control. So it's just say it's a control variable. I will. 6.5, we can say it's for control purposes. You can just say for control. Or you can say it's the controlled variable. Okay, control or controlled variable. Whatever you want to say, be familiar with some experimentations, okay? Because, yeah, they are mark-worthy. Now we're told the homologous series to which compound X, Y, and Z belong were identified randomly, meaning we don't know which one, Z or Y or whatever, as alcohols, okay, as alkanes, and carboxylic acids. Right, so this makes a bit of sense now, because we can see these are definitely different. Most likely this would be X, isn't it? Because it's already a gas at room temperature, like a short chain alkane, like from 4 backward, butane, propane, and ethane, and methane. They are all gases at room temperature. But once you start to have 5 carbons and more, you start to form more liquids, and so on. So the next one, I mean the one with the higher boiling point, is alcohol. So this should be Y. And then Z should be the carboxylic acid, isn't it? Because it has the highest boiling point. As you know that there's 2 sites for action of hydrogen bonds, which are responsible for those high boiling points, compared to alcohols, which only have 1 site for hydrogen bonding to take place. Here it's only weak van der Waals forces, which explains why it has a low boiling point. Now let's answer the next question. Now 6.6.1, which compound X, Y, or Z has the carboxyl group? Remember, what has a carboxyl group is a carboxylic acid, so it's going to be compound Z. Again, so we've got 6.6.1, so it's going to be Z. Highest boiling point because of 2 sites for action of hydrogen bonds compared to others. Makes sense, ne? 6.6.2. Okay, guys, we're already out of time now. This is when you are going to be told you have 5 minutes, guys, to finish. But I've taken the liberty to explain a thing or two, so that's why I'm behind time. Now explain the answer in question 6.5.1. I mean, they probably meant to say 6.6.1. Why are you choosing Z? We can say, basically, you can just say there are 2 more sites for hydrogen bonding between molecules in carboxylic acids. Okay, number 1. There are 2 more sites for strong. Maybe let's put the word strong, because the strength of the bond is what determines what we had an idea about. So there are 2 more sites for strong hydrogen bonding between molecules in carboxylic acids, meaning therefore more energy is required to separate molecules. All right, hence the highest, hence a highest, maybe let's say there, hence it has the highest boiling point compared to the 2 others. Okay, so I mean, you're just trying to be as comprehensive as possible, because I mean, it says explain the answer, 4 marks. So 4 marks is important here. What is important is the strength of the type of a bond, okay, and the energy requirement to separate molecules, and therefore the logical connection with the higher boiling point. Okay, and then now we can say the 4th mark is to note that there's actually 2 more sites. Perhaps I would give you a bonus mark there to make up for the 4 marks. Of course, keep it brief, keep it on point. All right, guys, that's the end of this question. So let's move on to the last one quickly. I've already lost time. Okay, so question 7 says, the flow diagram below, the letters A, B, C, D, E, and F represent organic reactions. Please, guys, for organic reactions, for me, know the type know the types, know the names of the types, know the reaction conditions. I will just say RC. If you remember these, believe me, you're gonna cruise through these things. If you know the type of a reaction, you know the name of the reaction, and you know the reaction conditions, you will definitely nail it. Now let's have a look here. What is going on? It's usually safer to start with the central compound. Okay, so we have an alkane at the center, an alkene. Okay, but now this alkene is going on to form an alkane. So what can we do there? This is an addition reaction. Okay, an addition reaction. In particular, if you were to give it a name, we hydrogenate it. And remember, with hydrogen, you need a catalyst like platinum and stuff. Okay, so remember that it is stuff like that. So, but I mean, you don't want to write details also. You just want to bring everything closer together so that it's easier to answer the next question. Now, let's look at B. B is giving us a 2-chlorobutane. So the 2 there gives us the position of the chloride atom, which is the halide. Okay, so it says it's in carbon 2. Okay, now what happens with this one? It's going to an alcohol. So when you're taking a haloalkane to an alcohol, you are basically doing a substitution reaction. Okay, it's a substitution reaction, and then of course this one is essentially called hydrolysis. Okay, and then please remember the reaction conditions. To move from this to that, you need a dilute strong base like potassium hydroxide, you need mild heat, and also you need alcohol, which is ethanol, as a solvent, because this is largely hydrophobic, right, with just a partial polar from the the chloride ion. So it's partially soluble in water. So now for you to be able to create an entire substance, you need to dissolve it in alcohol, then treat it with a dilute strong base like potassium hydroxide, and then add mild heat. You will form an alcohol. Okay, easy stuff. And then now we're looking at reaction C. Reaction C, let's come here. So we've got an alcohol here. So we've made our alcohol. So what do we want? So now we're going to do stuff like that, because now we have to jump around. Now we're moving from this to an alkene, so it means we must have done an elimination. So that's an elimination reaction, but this one, we removed water out of this to make an alkene, so it is dehydration. Okay, we dehydrated it. Okay, great stuff. And what else can we say? I mean, here, yeah, let's just leave the stories now. Let's just not talk too much. We are fine here, but here, to do this, to move an alcohol to an alkene, you need a concentrated sulfuric acid, isn't it, as a catalyst here. You want a dehydrating agent. So you may think about the condition that for this particular one, you need H2SO4 that is concentrated. That's just a condition here that you may need. Okay, let's look at the next one. D. What is the story about D? Okay, now D, we're moving from an alkene to an alcohol. So again, we've done an addition reaction. In particular, if you're adding water, you're going to call it hydration. So this is dehydration, hydration. Okay, easy stuff. Let's look at E now. What can we say about reaction E? This one, we can see that, okay, we are moving from a 2-chloropentane to an alkene. Again, it's an elimination reaction. I'm just going to say ER. And what is the name of this elimination reaction is dehydrohalogenation. We're removing the hydrogen halide. So we can call it DHH, dehydrohalogenation. Okay, I'm just trying to save time. Again, remember the conditions you need for this. You need a concentrated strong base, okay? You need to treat this with alcohol as a solvent, and you need mild heat as well. And then let's look at reaction F. Reaction F, we're moving from an alkene to a haloalkane. So we must have been doing an addition reaction. Okay, maybe let's choose a unique color for it as well. So this is an addition reaction, but this one is hydrohalogenation because we're adding a hydrogen halide to end up there. Okay, now that we've scratched the surface a bit, I mean, we're not trying to do too many details, but we just want to remember a few things. Some of what we've just done may be answers to questions, so remember that. Now use the information in the flow diagram to answer the following questions. We've got 7.1.1. Now write down the type of reaction represented by A. So we can see that A is an addition reaction. Okay. 7.1.2. And then what are we looking for? Reaction E. Where is E? So reaction E, you can see it's an elimination reaction. Okay. Of course, here they allow you to faff around and answer incorrectly and say this is a dehydrohalogenation, but that is the name of the elimination reaction. So for me, it's not quite good. Okay. And then, of course, even this one, to say this is halogenation, I'm not happy. Sorry, hydrogenation. I'm not happy with that because that's not the question. We wanted the general type. Okay. Anyway, we move on. Now, name the type, okay, of elimination. Again, now you see you're saying type and you're mentioning a type again. That for me is tautology. So I would say, okay, guys, these people are not serious. I'm scratching that. It's not necessary. Name the elimination reaction represented by C. The name of that. So when you look at C, it's an elimination definitely, but what is it? Dehydration. So it's dehydration. So 7, 2, 1. Here went. So this is dehydration reaction because we see we are dehydrating an alcohol to an alkene. Okay. Now name the addition reaction represented by F. We can see that this is hydrohalogenation. Okay, so that's easy. Again, they are sometimes confused too, so it's not only you and I who make the mistakes, they make them. So this already says poor moderation of the papers. If I'm the trusted person to do the examinations, whatever I say is accepted without being put under scrutiny, and that's bad practice, okay? Because it really tarnishes and degrades the level of our education. And yet, this is a good education. Don't hear people rant on social media and say this education is useless. what can you do, wada. Come on guys, it's just nonsense what they're saying, because have they realized that this very same form of education is a stepping stone to better performance as a professional in the future? And if you don't have this basic, you will actually poorly function as a professional, especially if this basic form of education is shaky. You will definitely suffer. That's why we have incompetent professionals today, because they never learned the basic education properly. This basic education is even stronger for me than our curriculum back in the day. It was much narrower, but at the same time, it was not inferior, because it had all the basic tools that are necessary to bring out a reasoning individual. And in fact, I feel like this one is too complicated even, because it almost tarnishes the intention of bringing basics into the surface of a student, because now you're just already putting too many complexities. Now this can make a bit of a confounded form of reasoning for a student, because it's easy to miss the point when something is too complicated. But as for inferior, no, I disagree, because you can become anything with this education. It only depends on you as a person, whether you pay attention for the sake of learning to improve your state of understanding and essentially your functional capacity. But if you just want to be a number, that I also have a degree, I also have a distinction, it's okay, you will get those, but you'll be useless at the same time, because you will have those distinctions, but you're not going to represent them with a high performance. Because what matters is practice, guys. It's not really the actual hypothetical examination. Anyway, I'm talking too much. I should not. 7.3, it says now reaction B. It's a substitution reaction, and then of course we saw that it's hydrolysis. Now it says write down the type of substitution. Now you can't say the type, but the name of the substitution. So that word type is incorrect, but we replace it with write down the name of the substitution reaction represented by B. So 7.3.1, this is hydrolysis, because we are forming an alcohol from a haloalkane. So do you see some of your brainstorming there is helping you to move quicker? And then again, me and my losing focus. 7.3.2. Now it says now two reaction conditions for this reaction. I'm going to list all. So one, you need a dilute strong base like potassium hydroxide, for example. It has to be dilute but a strong base. You need alcohol as solvent, because that thing is largely hydrophobic, or it's partially soluble in water, so it won't really yield the results if it is partially soluble, but it is completely soluble in alcohol. And then you need mild heat. Okay, so the reality is any two of these give you the marks. Okay, so the third one is just for you. Don't list three. The first two will be marked, and if by any chance your second one is an incorrect condition, then you lose marks. Okay, they won't look for the right one that is distant, so be careful of that. All right, now 7.4, besides heating under reflux, state the one other condition for ayiwena kutheni wangiqhela kabi awusafuni ngokwenza into zesilungu one other reaction condition for reaction E. Now let's look at reaction E again. What was it? Reaction E is a dehydrohalogenation, so we know that we need a concentrated strong base this time. not dilute. We want it concentrated because we want it to kind of eliminate. So we need a concentrated strong base, okay, which is KOH. Because they said 1, but you can add the second one, that you need alcohol as solvent. So any one of the two is the mark. You don't list both, okay? If you list both, the first one is the one that they will mark, and if by any chance the first one is a wrong condition, you are down, okay? Now, using condensed structural formulae, write down a balanced chemical equation for reaction D. So let's look at D. So we're moving from an alkene to an alcohol, so we need to hydrate this thing. But now we need to know, okay, how is this alkene? It comes from here. So we have a few rules up our sleeves to answer this question. So we know that we had a 2-chlorobutane, so 1, 2, 3, 4. So there was a chlorine here. Those are hydrogens. Okay, you have to start where it begins. Of course, they are letting you sweat because they know you're not gonna see that easily. So now we started with a 2-chlorobutane, all right, which is the structure. And then we went to an alkene, okay? Now, with an alkene, it means we dehydrohalogenated it, isn't it? So it means we're losing our friend here. And we're going to lose a hydrogen, but which hydrogen is it? Now, remember, we're using the rule of Zaitsev. So it says the hydrogen with the least number of, the carbon with the least number of hydrogens. This is where we will steal the hydrogen. But of course, this one has 2 compared to this. But remember, we can't eliminate 2 substituents from the same carbon, because once we eliminate 1, it becomes more of a secondary carbon. It has a bit of a relative attraction to this. It sort of refuses and be like, no man, can't do it. So of these other carbons, the one with the least number of hydrogens, except this one where we already took out the chloride atom, it becomes this one. So Zaitsev's rule will say we will form a major product by a double bond there. So this means our structure is now 1, 2. Then here we're going to form a double bond, okay, between these two, and then we will have the last one. So we just need to keep that hydrogen, and then we're keeping just 1 because we lost something big there. All right, so this is the structure of our alkene. It's basically a but2-ene. Okay, we can still have a but1-ene. So this is a but2-ene. All right, now this is the guy we're going to hydrate now. So we are supposed to use condensed structural formulae. So now to do condensed structural formulae, this is going to be CH3, right? And then here it's going to be CH. So when you're condensing this, you're writing it like that. And then CH3. Okay, that's it. So we still have the same setup. And then we're just going to add water. Water is an inorganic compound. So inorganic compounds, you don't have to show the structure, because structural formulae in organic chemistry, they only apply to the organic compounds. So don't worry about the organic compound in terms of a structural formula. And then we're going to go on to form something. Now when we add water in here, so if we're going to say here plus the water molecule, of course we're going to think of the water molecule as a hydrogen, as something like that. Okay, now the issue is what am I doing, man? Yeah, man, you're going to look at it like that. It will have an OH, so it's going to break into a hydrogen and hydroxide ion. Why? Because water has what we call auto ionization, isn't it? Whose constant is 1 times 10 to the exponent minus 14. Yeah, when you see now, I'm telling you, these things are like that. So now this water will essentially now come and break this bond by adding a hydrogen somewhere and the OH somewhere. Now here we're using Markovnikov's rule. That is when you're doing addition reaction. So where do we add? It says we're going to add the hydrogen to the carbon with the most hydrogens. Okay? And we're going to add this OH minus to the one with the least, isn't it? But the problem is that these two are pretty much one and the same thing, so to speak. So our issue now is to say we can put the OH anywhere and the hydrogen anywhere. It should be okay, but because we know that there was a chlorine here, we're just going to try and put it there so that it's not too bad. Okay, so this is going to be CH3 CHOH, okay, because we're putting this hydrogen in this carbon. Okay, and then CH2, because now this is going to acquire an oxygen, a hydrogen, CH2 and then CH3. That's it. So that is how you do this one. So this is our answer, guys. Forget about the other stuff. Okay, that is our answer right there. The rest was just our way of working that answer out. So how many marks you are getting? You're getting a mark for the structure. You're getting a mark for the, reagent that was needed. You're getting a mark for this guy. And of course, your chosen position of your OH. But you could still put it on this carbon and leave that one. It would be acceptable because now this is kind of symmetrical. These two are symmetrical, because if they were asymmetrical, we would know what to do. But now this is a bit symmetrical, so it kind of says you can either do it here, you can either do it there. No biggie. Alright guys, so this is the end of the video. I hope you've enjoyed it and you have learned something, and I hope it also helps to give you a bit of a full and comprehensive review of a question paper and how you may want to go about it. Of course, I've given extra information throughout. You don't really have to do as much detail as I have here, but these are some of the things I'm trying to stimulate to milk out of your materials as you study, and exactly how to practice doing a question paper. I think if you practice it like this, you are definitely guaranteed a decent mark. Of course, mistakes do happen. Sometimes you forget. A lot of things can deter you from getting a distinction. But I can tell you a decent mark like a B, a 70, 60 to 70 is something you can get. This is now while you're starting out. But by the time you're doing your June exams, if you're consistent with this technique, you are definitely guaranteed a distinction, all right? And I can assure you, you might score 100% by the time you're doing your trial. And obviously, you're going to just slide into 100% in your finals. That means you will have a strong portfolio mark. You guys are calling it what now? An ICAS mark or something like that. You will have a strong mark, and you can have a distinction at the end of the year. If you score a distinction in your trial and you score a distinction in your final, you're more likely to just be granted your 100% and they forget about your ICAS mark, because it will also be a good mark as well. Enough to say it's fair to give you 100% so that you are spectacular. But at the same time, even if you didn't get the 100% in your final, because mistakes are there, you will see that I commit a lot of them when I analyze these papers. But for me, it's just because of carelessness, because I'm too comfortable. But for you, a student, you know that it matters, so you will always be more vigilant than I should be. So in the end of the day, guys, you can really get a distinction. You can even score a spectacular mark if you want, but it will depend on how you go about your work? Do you prefer quick answers versus elaborate answers that take a bit of time while you are learning? Or are you already a fast student who actually can just, I just want an answer because I already know the rest. So you decide which type of a student, but this caters for any type of a student to become a beast. That's what I know. I've proven and tested this technique because I've been applying it throughout my school career, and it worked. Otherwise, guys, we've reached 2 hours and 30 minutes. That was the target for me, and I hope it doesn't rub you wrong, but it fortifies your efforts. Otherwise, keep practicing, keep working. I have prepared a short course on sequences and series, so I should be presenting it in the course of this week. I hope you're going to like it and use it as a revision for maths. Otherwise, good luck and goodbye for now.